So let's wait for 5 more minutes to see if anyone joins, then we can start. I think that's the people will join. So welcome everyone. This is MSc 26 early 86 NPTEL tutorial session on semiconductor devices for next gen pets. More than more, the physics perspective. The course instructor is Professor Sudeb Dasgupta and Debashish from IIT Kanpur. So this time we are at week 7, right? So let's begin. The first question is asked that in the Schottky effect, the potential barrier at a metal semiconductor junction is lowered due to what, right? So first we need to understand what Schottky effect is. So Schottky effect is also called image force lowering effect. Okay. So for first, let us consider a metal vacuum system. So in that case, we'll be able to appreciate what this barrier lowering is. Right? So let's say this is a metal. So this is metal. Let's say this is the barrier. And this is the junction or the end of metal. And then we have vacuum. And let us also define the axis system. So Let's consider that this is the x direction and this is the energy. Okay. So, and now let us draw the bands for metal. So let's say this is the vacuum level. Okay. That is E0. And let's say this is my EFM or Fermi level inside the metal. Right. So this distance is Q phi m. Right. Let us. So this is my Q phi m. Okay. So in case of metal, we know that this EFM is EC, EV, all right. So electrons are generally at this position. So if so, electron inside metal needs Q phi m, or that is the work function of the metal, this amount of energy to go into vacuum. Right. So what is the energy barrier now? So energy barrier is at this moment this much, right? This is my energy barrier. Okay. So this is the energy barrier. Fine. Now let's say we have an electron at this location. Okay. Let's assume this distance is x. Fine. So by laws of electrostatics, we know that this electron in the vacuum will induce a positive charge on the metal surface, right? Positive charge. And this distance is x. So what about the attraction force? So what about the attraction force between these 2 points? So it can be assumed that inside the metal, the positive charge lies just like the image if we consider the midpoint as an axis, right? You can consider this is my positive charge and the force due to that will be the electrostatic force. That is my, let's say this charge is Q minus Q. So this charge will be plus Q. So this will be minus Q square divided by 4 pi epsilon 0 times twice of x whole square, right? So this will be Q square divided by 16 pi epsilon 0 x square. Fine. So now can you tell me the potential energy for this? How do I calculate potential energy? Does this make sense, this definition?
Yes, sir.
So to bring one unit positive charge from infinite to a distance x is the work done. The work amount of work done is the potential energy, right? So this can be computed. So this is if infinity to x. So minus q square divided by 16 pi epsilon 0 x square dx will give me minus q square 16 pi epsilon 0 x, right? And how does this potential profile look like? This is a hyperbola, right? So this is my energy axis. So, and this is 0 or the vacuum level. So it will look something like this. It is rectangular hyperbola, right? Is that clear?
Yes, sir.
Now, this is so far we have not considered presence of any electric field apart from what will be, there will be one electric field present from this to this, right? Now assume that we have some external electric field in this direction. External, okay? This is external electric field. Now, what will be the potential energy of this charge due to this? So that potential energy will be, so in other words, how will this PE of X? So in presence of external electric field, let's say E of X, let's say it is constant. So how will it be? So this will simply add up to be minus q square 16 pi epsilon 0 x minus q times this times x. Does that make sense?
Yes, sir.
Right? Because it is a constant, so my potential energy will simply be the integration of that. Right? Now, if I draw this component, and let me just use this color for this. So this component will be something like this. So this is my term 2, this is my term 1. Okay, this is my 1 and this is my term 2. Fine. So now how will PE of X look like this quantity? How will this guy look like? Let's make it red. How will this look like PE of X? I'm just drawing, you can confirm. It will look something like this. Does that make sense?
Yes, sir.
Or let me use a different color altogether. So it will look something like this.
So this is the potential energy you're talking about.
Yeah, I'm only talking about potential energy.
Okay. Sir, but why must it actually have an asymptote, sir? At that y equal to minus xi.
Y equal to
Sir, I mean, why does it have an asymptote at that at the equation 2 line, sir?
equation 2 line. See, we have one part, one Roman 1 and Roman 2. Which one you are talking about?
Roman 2, sir. Roman 2. Why does
Roman
it have
2,
an
right?
asymptote at that?
Okay. So let's say we have a charge
Hmm.
plus Q, right?
Hmm.
And some electric field external. What will be the potential energy?
QE.
QE, right?
Hmm.
QE times distance, right?
Yes, sir.
That is because electric field is volt per centimeter. You
Hmm.
understand, right?
Yes, sir.
So this is that component.
Hmm.
That is due to the external electric field,
Okay.
and this is due to the image force.
Okay. So
S-
it's a
So
superimposition of the
it is
lines of
just
the wrong point of view.
superimposing, and
Okay.
mind that both have negative signs.
Okay.
So the more negative one will dominate because it is getting added in the negative axis.
Hmm.
So that is why, okay, just let me then mark this point as well at this moment. Let's say this is x of m. So below 0 to x of m, my green line dominates, right? It is more negative. So that is why the thick blue line is following that. And above xm, it is following the other potential energy that is due to the external potential energy.
Okay, sir.
Fine.
Yes, sir. Understood.
So now understand very carefully that if this term is not present, then how will my potential profile look like? It will be just this,
Yes, sir.
right? And then what will be my barrier? The barrier is Q phi m.
Hmm.
Now, due to presence of another potential, my this overall potential energy is getting reduced. So the barrier is lowered by, let's say, delta phi amount.
Hmm.
Okay. So
Hmm.
the consequence of that I will discuss, but let's go step by step. Okay. So far, so far, is it okay?
Yes, sir. It's all right.
So now let's say this lowered amount I denote by Q delta phi. Okay. So earlier the barrier is getting lowered by Q delta phi. Fine. And this maxima is at the point x equal to x of m. So how do we calculate x equal to x of m? We just put dp dx equal to 0, right, to find the maxima,
Yes, sir.
and use this equation. So my x of m will turn out to be square root q over 16 pi epsilon 0 modulus E. That is the external electric field. Fine. And
Yes,
how
sir.
can I calculate delta phi? I can
So
calculate my
we can
q
actually
delta.
find out the value.
Hmm,
We can find out the value at x of m.
right. That is PE at x of m, right?
Hmm.
And this comes out to be q modulus epsilon divided by 4 pi epsilon 0. Okay. You can compute this. Very simple maths algebra, right? So now this is for metal vacuum system, right? And what is the vacuum epsilon 0? 8.854 into 10 raised to minus 14 farad per centimeter, right? Now let's say
Yes.
you have replaced vacuum to semiconductor, or let's say silicon. Fine. So
So
in
in
that
that case,
case,
epsilon naught becomes epsilon naught, right?
right. So this will become Q E over 4 pi epsilon S. Where your epsilon S you can simply write epsilon R of silicon, right? What is epsilon R of silicon?
11.7.
11.7. So what will be the square root of that? Greater than 3, right?
Yes, sir.
So you can understand that the potential barrier lowering is lesser in high K elements. That means if your epsilon r increases, is this delta phi or q delta phi decreases, right?
Yes, sir.
Fine. So this is on consequence. So now can you tell me that in a metal vacuum system, let's say this is one system and another one I have metal semiconductor contact. In which case image force lowering or this Schottky effect, this effect is also called Schottky effect, will be more pronounced?
Sir, metal semiconductor.
No, the epsilon r is more, right? So this
Okay.
lowering will be
Okay.
lesser,
Okay. Okay. So in that case, Q delta phi will be more in the metal vacuum system then.
right? So
Yes,
for
sir.
this case, let's say if this was my barrier and my final product is something like this in metal semiconductor system, this barrier will be lowered lesser, right? But that is why it is many times for the first order analysis. So this is the reason in first time analysis of Schottky contacts or MS contacts, we ignore this. Okay.
Okay.
So now the question is, now there is a question related to the last session. Metal semiconductor contacts, will it always be of Schottky type?
No, sir. It can also be ohmic type as well, right, sir?
Right, right.
Phi is greater than phi.
And also the type of doping, right?
So,
Fine. So where will this become important? So let's say if I draw the potential profile, let's say earlier my barrier was like this. Let us discuss it on the semiconductor MS quantum. So what are the type of transport? Let's say I have electrons here and electrons need to go to the semiconductor site. How will they can go?
sir, if the barrier was lower, then they can go.
So basically what you mean to say, it is over the barrier transport, right?
Mm-hmm.
What is this called?
Barrier height.
No, what is this kind of transport called? This is called thermionic emission.
Okay.
Okay. So this is called thermionic emission over the barrier transport, right? The same thing happens in case of your uh, subthreshold region MOSFET as well. From source to channel, only the high energy tail electrons travels, right? That high energy tail electron traveling is the same thing that I am discussing. We have all discussed, right? This is a symbolic representation that all the electrons are at this location. However, it will be distributed over the energy. So this is thermionic emission. Now, how will thermionic emission dependent on this? So thermionic emission, let's say J thermionic emission is proportional to exponential of this energy barrier by some KT constant. Okay. Does it make sense?
Sir, once again, sir.
So let's say what is J of E? This is current density. So transport is what? This is a transport mechanism, right? Transport
Hmm.
means what? Transport means flow of current, right?
Yes, sir.
Carrier, charged carrier are getting transport from one location to another location
Hmm.
causes current to flow.
Okay.
Now let's say this current density, this will be more if my barrier is lower, right?
Yes, sir.
And that dependency is exponential, similar to my PN junction. You
Sir,
remember,
why would
right?
it have to be exponential, sir?
In PN junction, you remember how will we compute that this is my, let's say, P side. So in PN junction, you remember, right? Let's say this is my EF, this is my P side, this is my N side, right? Now for carriers from this to this, they in forward bias, what happens? They cross over the barrier, again thermionic emission, or we
Hmm.
call it diffusion, magnetic area diffusion sometimes in different contexts. Now
Hmm.
what happens when you apply forward bias? This barrier lowers, right? In forward bias, this barrier is lowered. And how will that current voltage relation in PN junction? I is proportional to exponential of V by Vt, right?
Yes, sir.
So this V is what? In terms of energy, minus E by Q, right?
Yes, sir. E equal to minus K by
So
E by
now
Q.
do you see?
Yes, sir. Okay. I see now.
So you have to get a, see, there are detailed quantitative analysis of everything, right?
Hmm.
If I start to do quantitative analysis, I may finish only one aspect of the one question in 1 2 hour session. So
Hmm.
it is that is why I am giving you the qualitative understanding. So that
Hmm.
is what we generally lack, most of us.
Hmm.
Quantitative thing you will get in books as well.
Hmm.
So you have to get a feel for what is thermionic emission, what is diffusion, right? These both concepts are the very same thing, that is over the barrier transport, fine. And this over the barrier transport or thermionic emission is a function of the current due to that transport or current density is exponentially proportional to the barrier height with a negative sign. If barrier lowers, my current density exponentially increases, right?
Yes, sir.
So now, if this barrier, however minimum it may be, it is going into the exponential, right? So the impact on current density will be huge. So we have said that in case of vacuum, the barrier lowering is more. But in case of semiconductors, metal semiconductors, the barrier lowering is lesser. However, it becomes important when we consider the transport in case of this MS kind of contacts. Because my transport or thermionic emission, the primary mode of transport, is exponentially dependent on that energy barrier. If that barrier is reduced by, let's say, zero point 0.1 electron volt, my transport exponentially increases. You understand what I mean?
Yes, sir.
So that is why this image force lowering becomes important when you consider transport in Schottky barriers or Schottky contacts, right? But in your first order courses, you are generally uh, concerned about the electrostatics. Fine. Transport, primarily thermionic emission, must consider Schottky effect or image force lowering. Fine. So in the Schottky effect, potential barrier at a metal semiconductor junction is lowered due to interaction between the charges and their image charges. Fine.
Yes, sir.
Okay. So let's move on to the next question. Calculate the space charge width. So let's say this is your MS contact. Okay. And let's say this is the contact is of this kind. So this is my EF. Let's say for the time being, this is like this. And say this is my E0 and metal has E0, something like this. Or let's make metal work function more, and this is something else. So this is my E0. So E0 will be continuous, and inside the same material, E0 minus EC will also be same because my electron affinity is a material property. Fine. And this is also like this. So this is my EC in F. This is my EV. And the barrier, what I see is this. Fine. So
Sir.
again, the same question. I have shown the all the depletion. So what is the type of semiconductor? It is P type, right?
Yes,
So
sir.
and it becomes, if it is P type, it becomes how much? If it is it depleted or it is accumulated, inverted, how is it?
Sir, it depends upon voltage if you're applying, right, sir?
No. How can you say that? This is P type.
Mm-hmm.
Here the amount of P type and here the amount of P type. In
Yes,
which
it
case
will become, it
accumulated,
will
right?
become accumulated.
Right. So that and in that case, what we are doing wrong?
Sir,
This
I do not.
region, this region will be much smaller, right?
Yes, sir, for heavy doping.
Not for heavy doping. See, one hole carries 1.602 into 10 raised to minus 19 coulomb of charges, and one this negative ion also carries 1.602 into 10 raised to minus 19 coulomb, and one electron carries minus 1.602 into 10 raised to minus 19 coulomb. So this is smallest size wise. This is also very small, and this is huge. So what you need to have is the charge balance, right? If there is some negative charges, the positive charges around it should be, the overall charge should be balanced. So now assume that I have, let's say, 1 coulomb of negative charge.
Okay.
It will be better if I explain this with electrons. Okay, let's say minus 1 coulomb of negative charge. So how many electrons? So how many electrons are there in the metal?
-1 divided by 1.6 into 10 power -19.
So 1 divided by 1.602 into
Into 10
10
power
raised to
-19.
19 minus 19, right? So
Yes, sir.
around 10 raised to 18, somewhat 10 raised to 18, this 10 raised to 18 electrons, right?
Give or take, yes.
So what should I balance it with?
So it will be
1
balanced with
coulomb of
positive interest rate, sir.
positive charges, right?
Yes, sir.
So now 1 coulomb of positive charges. How can I get that?
So same number of holes we have to put, sir, or
Same number
probe.
of holes, right?
Yes, sir.
So holes will also be very small.
Yes, sir.
So this region in which the bands will bend will be smaller.
Yes, sir.
Now let's say I had 1 positive coulomb charge here and 1 coulomb negative charge here. Then
Hmm.
this many number of positive, let's say this many number of holes are present or positive charges are present. Let's say positive charges are present inside the metal.
Hmm.
And what about this? There has to be either negative charges can be supplied by either electrons or these ions.
Hmm. Yes, sir.
So 10 to the power 18 electrons and 10 to the power 18 ions. Which one will take more space?
Sir, ions will take more space, right, sir?
Right, ions will take more space. So that is why if you see in your MOS capacitor in accumulation or in inversion, the charge is almost like a sheet charge. You understand?
Okay, so it will be purely due to electrons, right, sir? Not due to these immobile ions, right?
If it is purely due to electrons.
Okay.
So moral of the story is if it is depletion charges take more space than
Hmm.
your electrons or the ions take more space than electrons or holes. So the
Okay.
accumulation charge layer or inversion charge layer will always be like a sheet charge
Hmm.
confined in a very narrow region because they are very small particles.
Hmm.
Fine. So moral of the story is depletion will be in the semiconductor only. Why cannot there be depletion inside metal? And what is the W depletion?
So root 2 epsilon s by EQ into ND into 25 FP, I think. No,
25
we have
FP.
EBI.
Here it will
EBI,
be VBI, right?
yes, sir, into
We
1 by
have
ND. 1 by
right.
ND plus 1 by ND.
In this case, it is 1 by
Yes,
ND.
yes, sir.
But by the way, why there cannot be any depletion inside metal?
So charges cannot exist inside metal, right, sir?
Because metal is an equipotential surface, right?
Yes, sir.
Right. So using this formula, you can easily compute epsilon SI will be 11.7 into 8.854 into 10 raised to minus 14. Your VBI is given as 0.67, 1.602 into 10 to the power minus 19. And your ND you will have 7 into 10 to the power 18. This much centimeter. Fine. You can compute and check that which one is correct. And important point to note that barrier lowering effect is ignored. And then after that, when you get your answer, you need to convert it to angstrom. 1 angstrom is how much centimeter?
So 10 power minus 8 centimeters.
Minus 8. Okay. So remember that remembering this formula helps you a lot. Okay. In case of debye length, this VBI will be replaced by phi t. In case
Sir,
of
for what?
MOS, yeah,
Sir, for what it will be replaced, sir?
for debye length calculation, right?
Or
Any
debye length?
for any devices. For debye length, your VBI will be replaced by phi t
Okay.
for a
Sir, but
doped
that's also
semiconductor.
one more case, sir, where I've seen VBA replaced by 2.5 FP.
That is when it will. So basically, if it is a MOS system, right? So this depletion width is nothing but it depends on the potential between these 2 points, potential difference between these 2 points. In case of MOSFET, what is this potential difference? This is your surface potential. At surface potential at 2.5B, it pins.
Okay.
That is why in MOSCAP, this is replaced by 2.5B. MOS structure, right?
Okay, sir.
And this equation also holds for PN junction diodes also. So remember, this only depends on how much my energy band bends. Okay. Because in case of this, there will be an oxide drop also, right?
Yes, sir.
So that is why you only consider your surface potential. So this is only at one place. But if you have to compute W depth, what you will use? 2 epsilon Si by Qna times surface potential. Okay. So, right. Increasing the doping concentration in semiconductor forming a Schottky contact will so
it will decrease the width of depletion region, right, sir?
decrease the width of depletion region. Fine.
Yes, sir.
Again the same thing, because in a smaller section I will have, let's say, 10 to the power 18. In case I have 10 to the power 18 Na atoms or Nd plus ions, in another case I have 10 to the power 17 Nd plus ions. So, and again, let's say I have minus 1 coulomb charge inside the metal. So 10 to the power 18 electrons we need, right? So in this region, I will get 10 to the power 18 Na atoms. For this, I may need some additional region to cover for that additional factor of 10.
Okay.
So that is why with increased doping, my depletion region shrinks. The reason is same. That primary reason you have to understand. Okay, I have removed the primary reason is that charges need to be balanced. Okay, it is not about the number of ions or number of atoms. Charges need to be balanced. 1 Nd plus ion give 1.602 into 10 to the power minus 19 coulomb. One hole also gives 1.602 into 10 to the power 19 coulombs. So if it is holes, then I'll need much more smaller area physically. If it
Okay.
is Nd plus ion, I need much larger region, depletion region. Now, if
Okay.
it, how come this will, now if Nd plus is increased, that means what? In per centimeter cube, I have more number of Nd plus ions.
Okay.
So that
Sir, if
means,
we, sir, I just want to ask one thing, sir. If we
hmm,
have more number of ND plus ions, won't that mean that it will be occupying a large amount of space?
no. See, space is coming in the denominator, right?
Okay.
It is the concentration. Densely
Okay.
packed. Nd plus increasing means in a small, same region, I am packing more number of ions. I am not changing the space.
Okay. Okay. So it's occupying a smaller volume.
Right.
Hmm.
It- It's clear, right?
Yes, sir. More number of charges in a smaller in that volume,
Right.
in a fixed volume. Okay, understood.
Exactly. And I need to balance my charges,
Hmm.
not the quantity or the region. The region will accordingly get adjusted.
Okay.
Fine.
Yes, sir.
So let's move on. Which of the following mechanisms are responsible for gate leakage in MOSFETs? Okay. What is gate leakage?
So
So
that means some amount of current flows through the gate, right, sir? When it should not actually.
we are concerned about DC,
Hmm.
right? In AC, anyway, current will flow
Yes, sir.
because it is a capacitor. C dV
Hmm.
by dt current will flow.
Hmm.
In DC case, let's say I have a MOS system. Mm, okay. Let's say this is my N plus and this is my P type, N plus poly. So this will be EC if, let's say, initially my E0 is same and both will have, let's say this is my EC, then this is my EV because both are silicon. In this case, my Fermi level is here EF, and in this case, my Fermi level is here EF. Now I join them. If I join them, make a single MOS system. So first thing will be I have a constant Fermi level. Then this is my EC. This is my EV. We draw the boundaries as well. This is my EV, let's say, and this is my EC. So if this is my EC, this will be my EV, and accordingly, this will be my E0. This will be my E0. So it will be something like this. This, then barrier, this should follow this. You understood the Venn diagram?
Yes, sir. We did it in the first class also, right, sir?
Right, right. So if that is the case, then how will your current can flow between metal and semiconductor?
Sir, in this case, it won't be flowing, right, sir? Because the Fermi level is not bending. At least in the conventional sense, it should not flow.
Okay, now let's say you are reducing this further. Okay, you are reducing this further down, and you have applied some sort of bias. So let's talk about only one band. So this is like this, 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 and something like this. Okay, let's say this is my EC, and this is also my EF here, and in this case, my EF, let's say, is somewhere here. So now I have bias. This is applied VGB, let's say. Now can carrier move from one place to another?
Yes, sir. There's a band discontinuity, right, sir?
Let's say you will have electrons here, right?
Hmm.
That are your inversion charges.
Hmm.
And here also in metal, you can have vacant states for electrons to go. So can electron go from this place to this place?
Sir, but it's still a barrier, right, sir? How will
There
they?
is a barrier, right? So there is a thermionic emission present, but very less.
Hmm.
So what are the other mechanisms? Because
Sir,
understand that
tunneling. Sir,
for
tunneling, sir.
tunneling, right? For
If
current
the
to
oxide
flow,
thickness was very small, then it's possible they could tunnel.
right? Let's say this is my VGB, some bias VGB. Okay. So this is my IG. So for the gate current to flow, I need to have a closed path, right?
Yes, sir.
I need to have a closed path for current to flow in this system. That means what? That means I need somehow carrier movement across this region.
Yes, sir.
That means somehow I need my electrons to come from this side to this side.
Hmm.
Now, if this barrier is very small or narrow,
Hmm.
okay, let's say this is TOX. This is TOX, right?
Hmm.
Oxide thickness. If this TOX is very small, then these carriers can travel through by a mechanism called tunneling.
Like,
So, what is your depth of understanding tunneling? How does it happen? So,
somehow,
have you gone through
I don't
any
recall the exact
quantum
mechanics of how it goes tunneling. I
quantum
just
quantum mechanics course?
yes, sir, but I don't remember the exact
No, not exact.
surrounding.
So you remember, right, that
Yes, sir.
if
In
there
the
is a
area.
potential barrier,
Hmm.
electrons move, decay, then move.
Yes, sir.
So this is nothing but your potential wave, probability wave.
Hmm.
So if this is non-zero, so that means probability of finding electron in this potential barrier is also non-zero. That means if we consider the wave nature of the electron and this tunneling probability is exponentially dependent on this thickness, right? And also
So
it
lesser
depends on the
thickness,
electric
more
field.
probability of tunneling.
Hmm?
Lesser thickness, more the probability of tunneling.
Yes, lesser thickness, more the probability. So for thin oxide devices, we'll see why we need. So first question you should have, why do I need, why I am lowering TOX, right? That we'll answer later. Now for assume that for some reason we are lowering the TOX. That means my gate current will start to flow. Okay. This is a huge issue in our MOS systems. Why? Because if the potential across something controls the current across it, I am losing my field effect, capacitive action, and it is becoming an resistor, right? Which I do not want. I want a transistor action. High impedance at one node, low impedance at the other node. Right?
Yes, sir.
So this tunneling can happen if you have observed that depending upon, let's say, I have two layers here. So tunneling can happen from this to this. This
Okay.
part of tunneling is called, just let me draw it clearly. So let's say you have something like this, and in another case, you have something like this. So this tunneling we called direct tunneling or band-to-band tunneling. Okay. Another form is called BTBT, band-to-band tunneling. There is another way that can the electrons can or the carriers can tunnel is like this and then come down here by means of, or in other way it comes to this and then right down the hill. This kind of tunneling is called polar Norden tunneling. Okay.
Okay.
So what are the difference? Difference is the shape of the potential barrier. In one case, we can fairly approximate this as a rectangular potential well or trapezoidal potential well, right?
Yes,
In
sir.
other case, it is triangular. So your calculation changes a little bit, but the concept remains same. Fine.
Yes, sir.
So these two are the tunneling mechanism for which you generally have your gate leakage current. So understand one thing. So your structure is like this, right? This is your gate. Then you have oxide. And then you have your source and drain. This is N plus, let's say this is also N plus, this is P. So in any case, if gate current has to flow, it has to cross this oxide layer. So current conduction through oxide can only be possible by means of tunneling, some sort of tunneling. Okay. Because this guy is very less. So gate current or gate leakage are associated with multiple tunneling mechanisms. It can be BTVT, it can be Fowler-Nordheim, it can be Poole-Frankel, it can be TAT, many things, trap-assisted tunneling. These two, today's lecture we may not be able to cover. So just I'm giving you some brief. So let's say your potential profile is something like this.
So these are all various tunneling phenomena, right, sir?
Yes, various
Different.
tunneling phenomena. So let's say you have some defects here between the oxide, which is quite common, right? Then you have first you need to tunnel to this and then to this. This type of tunneling is called Poole-Frankel. Detailed analysis of these are present, and very honestly speaking, the analysis is very simple. So tunneling between, so just some additional things if you are interested. So let's say there are 2 points, point A, point 2. You need to find tunneling probability. It will be dependent on vacant states here, right? And field states here. Okay. It will be the product of two. Let's say F1 of some energy times F2 of some energy, and not F2, it will be vacant state, right? So 1 minus Fermi function of E2.
Yes, sir.
This is intuitively clear, right?
Yes, sir.
And you will multiply this with density of states, and then you will integrate it over energy. That is how you get tunneling probability. So these are just simple mathematics with a little bit of intuition. Okay, then you can get every form by considering different type of potential energy. You will get different type of form.
Mm.
So a good reference of this can be, you heard of this book SMG,
Yes, sir. I have the full name.
Physics of Semiconductors. Okay, third or fourth edition, whatever you can get. Fourth edition you may not get, but third edition you will just check the MIS cap chapter. I'm not sure. I think it is chapter 4 in third edition. So you can check that. There you will get these expressions. You may not get the derivations, but these expressions. Derivations are easy to do.
Mm.
Okay.
Okay, sir.
So next question is DIBL. How does DIBL affect threshold voltage of a MOSFET? What is DIBL? What is the full form?
So it's some sort of barrier lowering effect, right, sir?
Drain-induced barrier lowering. Okay. So we will consider this in a little bit detail. Let's say this is my MOS structure. This is my source. This is my gate. This is my drain. Right? And I want to plot the band diagram at this location. How will it look like? Let's say VGS equal to VAB and VDS equal to 0 volt. The band diagram across this line will look something like this. We are only considerate about. So this is source, this is channel, this is drain. Is it clear? This is N plus type, this is P type, this is N plus type. Just
Yes, sir.
PN junction band diagram.
Yes, sir.
Fine.
Oh,
Now, okay. So, let's say this is my case 1. Okay. So this is plot 1. Now let's say case 2, VGS equal to VTH, VDS equal to 0 volt. So how will my band diagram look like?
sir, in that case, the region one will lower, right, sir? Because we are applying a positive potential.
It will be, let's let's make it this. It will be like this, right?
Yes, sir.
So what happens? The carriers at this location in case 2 can easily
Mm.
cross the barrier, right? Because the barrier is lowered.
Yes, sir.
But will it cross?
No.
Electron can cross barrier and move to channel
Mm.
and to drain. So this barrier, what barrier we are talking, consider it about? Source channel barrier. Okay.
Okay. Sir, the Fermi level will also be lowered, right, sir?
No, why will Fermi level be lower? I am considering only x direction, right? And let's say this is my y direction. So in x direction, why the Fermi level will change?
Sir, we are applying a potential to the gate side, right?
So Fermi level will be here. It will be here, very close by.
Mm.
So let's say the Fermi level will be in this case here, here, and in this case somewhat here. Okay. This will not be exactly continuous, but it will be fairly similar.
Okay.
My drain to source, see, this is in the x direction, right? In the x direction, my VDS is equal to 0.
So which case are you talking about, sir? Case 1 or case 2, sir? About the Fermi level.
Let's consider a simple case. Let's say this is my Fermi level,
Okay.
EF.
Mm.
Fine.
Mm.
I am applying VGS. Why my EF across X will change? EF across Y will change. That I am sure.
Ah, yes, sir. So
But why
it's
will
because of
EF?
that region current will flow, right, sir?
Hmm?
So it's because of that region. It's because of that reason current will flow, right, sir? Because Fermi level at Y will change.
No. Current is flowing in the y direction or in the x direction.
It will be flowing in the X direction.
So what is your drift diffusion equation tells you?
That must be Q dP by dP by dx, right,
No,
sir?
no. That is not drift diffusion equation. So drift diffusion equation, what does it tell you? Jn is equal to Q mu n
N into E.
dEfn by dx.
Okay.
Qn mu n this.
Hmm.
So this will give me what? Q times E, right? So this will not be present. Q will not be present. It will be this Jn. This is the quasi-Fermi level, right?
Yes, sir.
So if my VDS is equal to 0, if my VDS is equal to 0 volt, so my DEFN by dx will be 0. So Jn will be 0. So why will there be a current and why will there be a difference? If I would have plot my band diagram in this direction,
Hmm.
then you would see the Fermi level to change because I am changing my gate voltage.
Okay.
But in this case, my VDS is 0, right?
Yes, sir.
So why will there be a change in Fermi level?
Okay. Sir, I'm talking about a case when it is greater than zero, sir, like VGS equal
No,
to
but
VT.
we are considering now VDS equal to 0, right?
Yes, sir. Okay.
So in that case, my Fermi level will be constant.
Sir, in all cases, will it be constant, sir?
Right, in our case, it will be constant.
Like
See,
regardless of value of VGS.
regardless the value of VGS. See, have you seen this Fermi level is not a 1D line, right? It is a 2D surface.
Okay. It will be extending in the back direction as well, right, sir?
Ah, so it is changing in the y direction. It with VGS in the y direction, EF will change. But in x
Okay,
direction, why will it change?
okay, sir. So the EF at Y direction will change when we apply VGS, right, sir?
So in y direction, how will it look like?
Sir, generally
It will
speaking,
look
when we
like,
apply a positive potential, the Fermi level will lower, right, sir?
right, Fermi level will lower, but you are applying positive potential at which place?
At the gate side.
Right, and what is the Fermi level you are talking about? In which direction?
That will be the Fermi level at Y.
Right. So this is across this direction, right? Let's say this is B bar.
Hmm.
So this is B bar. Band diagram across this direction.
Okay.
If it is oxide, it will be like this. And let's say this is your Fermi level.
Hmm.
So it will change.
Hmm.
And as you are applying positive VG, so this will go lower, right?
Hmm.
So this is your EFM and this is your EFS.
Hmm.
So in this case, it is changing because now I am drawing this in the y direction.
Okay.
But where I am plotting this, I am plotting this in across this line.
Okay. Okay.
Why will it gate will change the Fermi level across this line? Because across this dashed red line, the potential is same. My VDS is 0, right?
Yes, sir.
So Fermi level is same.
Okay, so it's only in the y direction it changes, I see.
Exactly. So that is what I wanted you to visualize first.
Okay.
That we generally draw our band diagram in this direction. So that is where this concept confusion comes from.
Hmm.
Fine.
Okay, sir. Sir, but in the first band diagram which you draw, won't there be an X and Y direction actually, sir?
Which band diagram?
The first band diagram which you draw, the first one.
This one?
Oh, yes, sir. That one only. Yes, sir. There'll be
That
an
is
X.
in the X direction, right?
Yes, sir. Sir, but won't there also be a Y? I thought there would also be a Y direction for that band diagram, sir.
Yeah, there will be a Y direction for that band diagram.
Okay.
There will be a Y direction for that band diagram. But you
Hmm.
see, so the issue is that issue with the visualization with graph. So what is this Y? This is Y is at a fixed point, right?
That would be Y equal to 0. Okay, yeah, it will be Y
Let's
the
say
fixed.
let's say some Ys.
Hmm.
This is Y equal to 0. It is some Yx. So Ys is
Yeah.
fixed.
Mhm.
So in this Venn diagram, Ys is a single point,
Mhm.
and I am changing x, right? It is a 2D plot.
Mhm.
Is it clear?
Yes, sir. Now it's clear now.
Okay. So coming from this, now consider a case 3, where your VGS is equal greater VGS is equal to VTH, let's say, or greater equal to VTH. Yeah, let's say equal to VTH, it will not matter. And VDS is greater than 0 volt. How will my band diagram change?
So in that case, won't channeling modulation come into effect? So the depletion
No, no,
region will start
don't
increasing.
don't don't go to those things.
Okay.
So I am only concerned about EC. So EC will change
Hmm.
like this, right? And maybe bending will start from somewhere here,
Hmm.
because at more VD, my more depletion will occur at the in this
Okay.
region, right?
Yes, sir.
If
Sir,
that is
but
what
why
you
does
meant to say.
EC actually, but why does this EC line actually bend, sir? Is it because you're applying a positive potential on that thing?
Yes.
Okay.
And now what will happen, as you are telling that this is my EF, this will be my EF.
Okay.
Now there is a separation, you see? And
So
what
there
is
will
this
be a current flow.
separation? This is the VDS, the
Okay.
applied VDS, this separation.
Hmm. So now there will be a
Current,
current.
yeah, current flow will be there because
Hmm.
this is providing me an electric field, right? In this direction.
Hmm.
In earlier case, my electric field was 0.
Hmm.
So where will that electron go? Fine.
Hmm.
So, but by doing so, so by doing so, what about the threshold voltage? What about VTH? What does it depend on? Threshold voltage depends on barrier at this location. Okay,
Yes, sir.
this barrier. It depends on source channel barrier height. Why? Why does it depend on that?
Which also the VTH.
Yes, threshold voltage. So what is threshold voltage?
Well, threshold voltage is the minimum amount of gate voltage which must be applied so that current starts to flow in that
Okay,
in the
just
channel.
let me write that down. Minimum amount of VGS required
To create
for
a
significant current flow. Okay,
hmm,
significant current flow, or as you said, create a
channel.
channel. So channel is created by what? Channel is created by VGS,
Yes.
not VDS, right?
Yes, sir.
And why VGS? Because this only changes the source channel barrier.
Hmm.
So you see, it is like this, right? Until unless, let's say, in some mechanism, I am reducing this barrier, okay? Let's say I am having this kind of profile. Somehow, will my threshold voltage change? My electrons, source of electrons are where? This place.
Yes, sir.
Until unless this electron, in this case also, in case 2 also, electron has to overcome this barrier, right?
Yes, sir.
So until unless this barrier is lowered or the source of electron is more, my carrier concentration in the channel will not change much
Hmm.
because my electron has to come from somewhere,
Hmm.
that is coming from the source.
Sir, so in both cases the threshold voltage will be the same. Is that understand?
In both cases the threshold voltage will be same.
As long as we need to cross that particular barrier, right, sir?
Yes, as
Hmm.
long as this barrier is undisturbed. Okay, now let
Hmm.
me just draw a zoomed version. So this is your case, right?
Hmm.
VDS greater than 0. This is my EC, and VGS is equal to VTH. Fine. Now what will happen if I keep increasing my VGS? Keep increasing my VDS. If I keep increasing my VDS, let's say it will be like this, right?
Channel width will reduce, right, sir?
Yes, that is what? That is your CLM.
Channeling modulation.
Fine.
Hmm. Sir,
But in
can't we also
no,
say it's due to
yeah,
being more reverse bias, sir?
it will be
So can't we also say the channeling modulation is due to the channel becoming much more reverse biased? Or at
what?
least the N plus region is becoming more reverse biased with respect to the substrate.
Yeah, that will also be the case.
Mhm.
See, so far in MOSFET analysis, we use this approximation, right? Gradual channel approximation. What is that? We assume that the electric field in this region, EY,
Yes.
is much stronger than
E into
EX,
epsilon X.
right?
Yes, sir.
But as soon as my this field also increases,
Mm.
this VDS increases, the electric field start to rise. So there are 2D fields. Okay. So this horizontal field is what you are talking about, this depletion region due to the PN junction, reverse bias PN junction. But similarly, you understand one thing also, if this potential is increasing, so the effective VG channel is reducing. That will also drop the inversion level, right?
Yes, sir.
So both things are happening. So you can understand it in this way initially, that the depletion region width is increasing. Fine.
Yes, sir.
So now, so far, VTH is not a function of VDS.
Hmm.
Is not a function of VDS, right?
Yes, sir.
This is true for long channel MOSFETs. Fine. Now and what is the channel length? This is the actual channel length. Now let us draw the same case for a short channel device. So this is my long channel case, and for short channel, so in one case, somewhere here is my channel length. So this is drain. This is source. This is channel. Okay. And there will be oxide here. But in another case, I have a short channel device where my drain is at this location. You see the long channel case and the short channel case. What is the difference?
Difference in channel length, sir. Hmm?
The red one is a short channel device, okay?
Yes, sir.
And the black one is long channel device. So what is the difference in case of, let's assume that in both cases, VDS equal to 1.8 volt. Okay. And this is the case at VDS equal to 0 volt. This is the case at VDS equal to 0 volt. So can you see that in the short channel case, the source to channel potential barrier is lowered? In all cases, VGS is equal to VTH, let's say.
Yes, sir.
Is it apparent?
Yes.
in long channel cases, when my drain voltage is increased, the drain side energy barrier is lowered, but it is not reaching the source channel barrier, right?
Hmm.
But in case of short channel devices, my source and drain are so close that when I pull down my drain energy barrier, the
Hmm.
source side energy barrier also gets lowered.
Okay.
So this particular phenomena is called drain induced barrier lowering. So what is the consequence? First consequence is that now VTH becomes a function of VDS.
Sir, could you explain the last part again, sir, for the drain-induced barrier lowering?
Okay. So in long channel device, this is my VDS equal to 0.
Hmm.
So as my VDS is increasing, this part is getting lowered, but my source to channel barrier is intact.
Okay.
That means my VTH is not a function of drain voltage, right? Now in short channel devices, this is my VDS equal to 0 case. Now
O-
as soon as I increase my VDS, my source to channel barrier reduces.
Okay.
This is because this channel length is lower, right? Basically, let's say your depletion region, let's say this region is, this spread is, let's say 1 micrometer,
Hmm.
and your channel length is, let's say 10 micrometer.
Hmm.
So in 10 micrometer, if you take up 1 micrometer, it will not matter, right? Still my source is 9 micrometer away.
Yes, sir.
But in case if it is my, let's say 1.5 micro or 2 micrometer short channel device, my depletion length will be same, right? At the same bias, same what does my depletion length dependent on? It is dependent on the bias,
It's
built-in
also the,
potential, and doping.
yes, sir.
In both the cases, my doping is constant for our case, for our
Hmm.
discussion's sake.
Hmm.
But now my 2 micrometer channel length, 1 micrometer is gone. So I am
Hmm.
very close to source now.
Yes, sir.
So basically my lateral field, this lateral field has to start to penetrate in my source.
Okay.
So that will pull down, because this is pulling down, right? By increasing VD. This is pulling down the energy barrier. So that is lowering the source to channel barrier.
Hmm.
That means
Sir, why
my,
is that purple arrow from the right to left, sir? That I didn't understand.
sorry,
Sir, why did you not have purple arrow from right to left?
electric field,
Okay.
horizontal electric field, right?
Okay, that is from the drain side, right, sir?
Drain side, yes. That is your horizontal E of X.
Hmm.
It is a drain plus this. So there will be depletion region. Let's
Hmm.
say VG is equal to VFB. Why till what point? Let's say I am drawing these three lines.
Okay.
This is my contact VDS.
Hmm.
So let's say this is X equal to this is X equal to X3, X
Hmm.
equal to X2, X equal to X1. This is X equal to X0, and somewhere here is 0. Till what point will the electric fields be?
Yes, sir.
My question is, this electric field, the blue lines originating from the drain,
Hmm.
will be non-zero till what point?
So till it reaches the source side.
No, why source side? It will be till the end of depletion region, right?
Okay. Oh,
Beyond
yes, sir.
depletion
Because
region, it
of
is
that
quasi-neutral.
negative ions. Ah, yes, sir. Because of the positive and negative ions, yes, sir.
Ah, right. Beyond that, it has no effect. The drain electric field has no effect. And
Okay,
why
yes, sir.
I have put Vg equal to VAB because my then that means due to vertical field, no charge is present. Flat band in y
Hmm.
direction. Right? It is
Okay.
only due to VDS.
Okay.
So it will be till the depletion edge. So in
Okay.
this case, till what point my electric fields are? My electric fields are in this case till this point, in this case till this point, in this case till this point.
Okay.
Is it
Till the
ever
negative
reaching?
width.
Yes, it is never reaching my source, right?
Yes, sir. It will not reach the source now.
But in case of short channel devices, my depletion region extending till source means my electric field is reaching till source.
Okay. Yeah.
That will pull down the barrier. You understand?
Sir, how will it actually pull down the barrier? I understood that it will reach the source, but why will the
It will
barrier
reach the
also go
source.
down?
That much. It will reach the source. That much you understood, right?
Yes, sir. That I understood.
Okay. Now let's say this is one case.
Hmm.
Fine. So, okay, let me explain it in long channel case only. So, in long channel case, is it pulling down the barrier here? Barrier in the sense of is the energy band is lowered?
Not exactly.
Why not lowered? It is lowered, right?
For the long
Earl-
channel case.
Earlier it is like this. I am ignoring the source part.
Hmm.
But as my VDS increases, how will my band diagram look like?
Will
Band
go
diagram
here.
will look like something like this.
Yes, sir.
So now if I take this point,
Okay. In that case, the band. Okay, yes, sir. The barrier will
it
be lowered.
right?
Yes,
Same
sir.
thing is happening in the source side as well.
Okay, okay.
It is just that this point is now very close to the source.
Okay.
Are you satisfied now that increasing VDS, the source side barrier will be lowered in short channel devices?
Okay, yes, sir. Now I think I understood.
Okay, fine. So this is the qualitative part of this. Okay.
Mm-hmm.
So now tell me what will happen to VTH
So that means the VTH will
if
be
VDS increases,
for short channel, VTH will be lowered.
source channel. These are all for short channel device. Okay.
Mm-hmm.
So short channel. If VDS increases, source channel barrier reduces. What will that mean to threshold voltage?
Voltage will
Increase.
decrease.
Threshold voltage will decrease, right?
Yes, sir.
So this is threshold
Voltage.
voltage lowering
Mm-hmm.
due to DIBL. Okay.
Yes, sir.
Now, how will this look like in your, let's say, output characteristics? Okay. So this is VDS, this is ID. And how will this look like? It means you need to see, right? You need to understand from the characteristics because you will only have access to the measurement data. You can only see, understand that whatever we are discussing, you will not be able to see in real world. This is
Mm-hmm.
the physical manifestation of 40, 50 years of research that
Mm-hmm.
people started to visualize like this. You will never see energy band diagram in real device. There is no energy band, right? It is just a tool to analyze the device. What you will be able to see in the oscilloscope is your ID versus VD and
Mm-hmm.
ID versus VG. So always remember whatever we are studying, we need to be able to map it to the output and transfer characteristics. Am I
Yes,
clear?
sir. Yes, sir.
So let's say this is your VDS equal to 50 millivolt. That means very small, okay? Linear region.
Hmm.
So in case of long channel device, how will VDS equal to 1.2 volt look like?
ADC 1.2 volt. It will be lower.
Wait a minute.
So it'll actually depend, right, sir? I mean, like, there might, at pinch of condition, I heard that this current
No,
become
no,
saturated.
don't see short channel effects. Understand this in superposition. Assume
Okay.
that all other short channel effects are off.
Okay.
Okay, only focus on DIBL.
Hmm.
How will my long channel device look like? Let's say this is my threshold voltage. Okay,
Hmm.
in case of long channel device, it will be simply like this. Do you agree or not?
I don't understand why actually.
So that is why I'm asking you. Try to visualize.
Hmm.
So what is the difference? This is my sub-threshold region, right?
Hmm. Yes, sir.
Below threshold, what is the impact of current on volt? What is the impact of drain current in voltage? My channel is not formed.
Not only from that. No.
My channel is not formed, right? So
Hmm.
whatever drain voltage I may apply, my current will not flow.
Okay.
That will be the same current. In
Yes,
case
sir.
of small VDS and high VDS, it will be the same current.
Yes, sir.
As soon as my channel forms,
Okay.
now once I am going from VDS equal to 50 millivolt to 1.2 millivolt or 1.2 volt, my device is going from linear to saturation. My current will increase.
Okay.
Understood?
Yes, sir. Sir, but the problem I'm having with this graph is, you said that below the threshold there will be no current, right, sir?
Consider no current means leakage.
Okay, so this portion below the sub-threshold, I take it as a leakage, right, sir?
Yes. Below
Oh,
subthreshold, everything is leakage.
okay. Now it makes sense.
Right?
Hmm.
And leakage mechanism also we'll discuss. That will
Hmm.
eventually come. So
Hmm.
whenever you are studying device physics, no, the first thing when you are studying it for first time, take one effect at a time. Don't mix up with multiple effects.
Okay, sir.
Superposition you can do. You have
Hmm.
seen in the first problem, right?
Yes,
If
sir.
you understood this and this, superposition you can do. It is just the addition of those two.
Hmm.
So this will be the case for long channel device.
Okay.
What about the short channel? So by short channel, I mean W by L, I am taking fixed, okay?
Hmm. But it will be decreased, right, sir?
So short channel device will be like this,
Hmm.
okay? So where do you see the threshold voltage decreasing? By the way, how do you calculate threshold voltage? You use constant current method, okay?
Hmm.
This is your constant current. Let's say I constant.
Hmm.
So what is the threshold voltage in second case? Red case is this.
Hmm.
In black case, the threshold voltage is this.
Yes, sir.
So you see that threshold voltage is being lowered.
Yes, sir. Due to DIBL.
Yes. So this red plot
Hmm.
is for short channel device. Fine.
Yes, sir.
Now what about output characteristics? So let's say this is your long channel case.
Hmm.
Your short channel case will be something like this, right?
Yes, sir.
Why so? Why this increase in current? Because your VTH is getting lowered. And we know that current is proportional to VGS minus VTH whole square,
Yes, sir.
right? So if VTH is decreasing,
The BGS minus VT
ID
will increase.
will increase and ID will increase,
Order increases, yes, sir.
right? This is why. So these are the signatures of DIBL, okay?
Okay, sir.
But you will say that my channel length modulation also shows same signature like this, right?
Hmm.
How will I differentiate? For that, you need IG also. In case of
Hmm.
channel length modulation, this threshold voltage will not shift.
Hmm.
Fine. So this is what your DIBL is.
Hmm.
So DIBL effect the threshold voltage, it reduces the threshold voltage. Okay.
Yes, sir.
By lowering the source channel barrier for short channel devices.
Hmm.
Okay. Uh, what this is something. Have you studied this earlier? What is Dennard scaling?
I've heard about it in the NPTEL slides, but I'm not really sure what it exactly is.
Okay. So Dennard is this guy. Okay.
Hmm.
See, remember that IBM, what you know today, hires for mostly IT firms from NITs are
Hmm.
have played a very important role in earlier semiconductor devices and still playing while their uh, current semiconductor research may be limited and very area focused, but IBM played very key role in developing earlier semiconductor devices, theories, computers. Okay,
Hmm.
so this paper is from October 1974.
Hmm.
So this guy, Robert Dennard, he predicted the or put up a law by which the MOSFETs should be scaled. You remember in the first class we have discussed that why scaling is important.
Yes, sir.
Means we discussed voltage scaling and geometry scaling, right?
Hmm.
So geometry scaling makes sense because I need more number of transistors on a chip, so I am reducing everything, and that increases my the L is reduced, my ion is increased,
Hmm.
speed is increased, many advantages, right?
Hmm.
But if I do not scale my voltage, what will happen?
Heating effect.
So voltage and length, my length is reducing, voltage is constant, so what is this?
It will lead to electric field, sir.
Electric field will increase.
Yes, sir.
And what
That,
happens when electric field increases?
that will break down, right, sir?
Exactly. There are many things that will happen before it reaches the breakdown point, but devices eventually breaks down.
Hmm.
So we needed what? We needed voltage to also get scaled. And this also plays into our favor. Why? Because if voltage is lesser, power consumption is lesser.
Yes, sir. So there's also the hidden advantage that we'll need only lesser voltage to turn it on, right, sir?
Lesser voltage. So see that that is dependent on, that is my threshold voltage, what you are talking about.
Mm-hmm.
The voltage required to turn on and turn off is threshold voltage. So
Mm.
threshold voltage has very little to do with voltage scaling. It is more to do with
Power
this
consumption.
length. If length is reduced due to short channel effects, my VTH will reduce.
Yes, sir.
Okay. So this voltage scaling is mainly for having the constant electric field.
Yes, sir.
So the basic idea behind Dennard's paper, this is one of the most important paper in, so this is one of the most important paper in semiconductors. Papers historically, okay. So he predicted electric field to be constant
Mm.
and charted out the way that semiconductor industry should determine what technology, thickness, doping should be. Okay. So length scaling we understand, width scaling we understand. Okay, both you are reducing by K. But what
Mm.
about TOX? TOX you also need to be lowered.
Mm.
Why TOX is needed to be lowered? Because your I is what? Mu n COX.
Mm.
W by L VGS minus VTH whole
So that
square.
we can get higher current.
Ha. So TOX
Sir,
also needs to be lowered.
but in that case, won't it also have a tunneling effect also, sir, if you are lowering the thickness of oxide?
Ha. Yes, absolutely right. It will worse. And
Mm.
that is why
It's
you
like a
need
double-edged
something
sword, right?
different. We will discuss that.
Mm.
So, okay. So I is dependent on what? I is dependent on Cox dash,
Thickness.
right? Not
Yes, sir.
Tox. So this is epsilon ox by Tox.
Mm-hmm.
So what if I reduce this, right?
Mm.
And to get same Tox, I increase this instead of reducing this.
Mm. So that means we'll have to move to some other material, right, sir?
Yes, that is what industry uses now. Industry uses hafnium, hafnium
Mm.
dioxide.
Mm.
Its K value is 3.9. Its K
Mm.
value varies from 20 to 26.
Mm.
Okay. This is
Yes.
called, we will discuss these things. Okay. This is called high K dielectric.
Mm. So is it necessary that only oxides have to be used for this? Is it necessary for
No, you can
insulators?
use, see, you can use anything, right? But the issue is that this is silicon. This
Mm.
is SiO2. So this
Mm.
is its native oxide, right? So
Okay.
the states in this region will be much less. The
Okay.
interface is more pure in this case. So even if
Mm.
you use HFO2, no, you will
Mm.
have a interface layer of SiO2, then you use HFO2. A
Mm.
very thin layer of SiO2 you will use, and
Mm.
then on top of that, most of the material you will use HFO2.
Mm-hmm.
But if it is something else, there will be interface states which will degrade your mobility due to surface
Okay.
roughness scattering. Because you
Okay. So.
remember that your carriers are flowing in this interface only.
Mm.
So your interface needs to be very clean.
Okay. Okay. So that's why we need to have such compatible materials, I see, and not just any
Ah,
random
exactly.
insulator.
Exactly. People have tried multiple things. Believe me, SiO2 is the best material for silicon,
Hmm.
being its native oxide.
Hmm.
Okay. So those things will be discussed later as well.
Hmm.
So this is why your scaling is required. Why doping concentration is required to be scaled by K? Any idea?
No, sir.
All physical dimension, all physical dimension have to be scaled by 1 over K, right?
Yes, sir.
So what is your W depth? W depth is what? Square root 2
Sir, here K
epsilon.
represents, sir, here K represents the Boltzmann's constant or dielectric.
No, no, K is the factor. Okay,
Okay.
good question. So K is the factor. Let's say
Uh,
uh, L1 by L2 is K.
okay.
Okay. So basically L2 generation 2 length is lowered by a factor K.
Sir,
Okay.
but isn't K the dielectric constant or is it just a scaling factor?
So your name is Ananta, right? There
Yes,
can be
sir.
multiple Ananta as well.
Yes,
It is
sir.
the same thing. K is just a constant.
Okay. It's not the scale. It's not the other one. Okay, understood.
Ah, so
Scaling
that
factor.
there are, see, there are, we have limitation of this, no.
Hmm.
We have limitation of notations. So you see, this K is Boltzmann's constant, but
Other one is kappa.
this
Okay.
kappa is unitless scaling constant. Okay.
Okay. Okay.
So yeah. So let's say this is surface potential, right? So
Hmm.
W depth needs to be scaled by 1 over K.
Hmm.
This psi s is scaled by what? Voltage is also scaled by 1 over K, right?
Yes, sir.
So to get W depth, a scale of this, what should Na be scaled by? Na should be scaled by K, right?
Yes, sir.
So that it becomes 1 over square root K square and W
Hmm.
depth becomes
One by
1 over
K.
K or
Yes,
scales
sir.
with 1 by K. So that
Hmm.
is why doping concentration also needed to be increased.
Hmm.
But what is the drawback of doping concentration increasing? Your mobility will degrade,
It's
right?
like for mobility falls. Mobility falls.
Mobility falls, right? So
Yes, sir. Because of
this,
the Coulomb
yeah.
scattering.
So this is 1974, remember.
Hmm.
But this constant electric field scaling has never been used
Yes, sir.
after, so for just only for some basic initial technologies. Okay. So that is why we used something called hybrid scaling.
Hmm.
I do not know if I will have time. If I have time, I will discuss this in the summary session. Okay.
Okay, sir.
So this is what then current scales with 1 by K. This will just put the formulas and check.
Hmm.
Okay. Delay Q by I, power
Hmm.
VI, power density
Hmm.
VI by area. This
Okay.
everything you check.
Hmm.
So there is another question that, okay, where is that question? Yeah. In technology scaling, a factor K scales down all the device dimensions, supply voltage, and capacitance. How does the power delay product change? So PDP is power times delay.
Hmm.
So power is V times I.
Hmm.
Delay is what? Delay is Q by I.
Hmm. So I will be cancelled, right?
So V and this is CV.
Okay. CV square.
So CV square,
Hmm.
right? What is
Hmm.
C? Epsilon ox by T ox.
Hmm.
Means it is just approximate analogy, right?
Hmm.
So Tox is scaled by 1 over k,
Hmm.
and V is scaled by 1 over k square.
Hmm.
But there is also C is what? Epsilon naught Tox times
V square
WL.
7. Okay.
We talk about absolute capacitance, right? In this case.
Ah, yes, sir.
So WL will give me
Another
1 over
case.
k square.
Yes, sir.
So this scales with 1 over k cube, right? This will go up.
So it will decrease by a factor of 1 k cube.
Okay, decreases by a factor of k cube.
So just one doubt I have to ask, sir.
Yeah.
So, why does psi s actually scale with k, sir? How does it become 1 by k?
Why? What is psi s?
Psi s is the difference between local vacuum potential and
Psi
point
s
limit.
is no. Psi s is the surface potential.
Yes, sir.
So surface potential.
Hmm.
So your VGB gate
Hmm.
voltage is what? VFB plus surface potential oxide drop plus
Hmm.
surface potential.
Yes, sir.
So in depletion, this is psi s times this
Hmm.
psi s. So your
Hmm.
VGB is decreasing with 1 by k. Why won't your psi s will decrease by 1 by k? Every term has to decrease by 1 by k,
Okay, okay. Yes, sir.
right?
Yes.
So that is how. So this thing, DIBL question, another DIBL question. So this paper, if you're interested, you can read.
Hmm.
Okay. So that is what Dennard scaling is. It showed the path of how to means design your next technology. Okay. So now today, if 90 nanometer technology to 45 nanometer technology, or to 90 nanometer technology to 65 nanometer technology, what are the consideration you should take? That is given by this. So what kind of doping you should use, what kind
Hmm.
of channel length you
Hmm.
should use, what is the
Hmm.
minimum channel length you can go for, what is the
Hmm.
oxide thickness, whether you will need high K dielectric or not, whether you need different channel profiles or not, right? This
Okay.
kind of things.
Yes.
So drain induced variable loading in MOSFET, decrease in threshold voltage due to gate voltage, no. Increase in threshold voltage, no. Causing mobility degradation, no. Reduction
Outside.
in the barrier height at source when drain voltage increases. This we have discussed, right?
Yes, sir.
Right. So GIDL will discuss next class. Okay.
Okay, sir.
This is another important phenomena.
Hmm.
This and channel length modulation also we will discuss
Yes, sir.
next class. Okay.
Yes.
I think that should be all for
Hmm.
today.
Hmm.
Okay. Thank you.
Thank you, sir.